This video is about weight and balance, and we're going to look specifically at the Cessna 172 weight and balance. Weight and balance, of course, determines every aspect of the aircraft performance. Operating outside of weight and balance degrades performance at best and can be catastrophic at worst. Weight and balance has to do with the balance of the aircraft when it's flying. The wings generated a limited amount of lift, which has to be greater than the weight of the aircraft. Maximum weights for ground operation, takeoff and landing, are set by the manufacturer. The effects of overloading the aircraft with weight will increase your takeoff speed and distance, will decrease your climb rate, will decrease your cruise speed, will increase your stall speed, increase your landing distance, and in flight, you can have damage structurally to the aircraft. The balance of the aircraft is critical because, as you see right here, the lift of the aircraft, all right, is generated by the wings, and the center of lift is what opposes the weight of the aircraft. The center of balance for the aircraft then is in a different place. It's basically the balance point between the tail and the engine, and it has to be slightly in front of the lift vector here, or the center of lift. It's very similar to, and I'll go ahead and see if I can get this to work. There's the center of gravity, and I'll put that up there. Putting this, the rubber band is in essence the lift vector, because it's what's holding up the ruler. All right. As long as it's balanced, it'll be balanced around the center of gravity. If I change the weight, now I'm going to move this out, you can see that the center of gravity, there you go, that's pretty good, is going forward. So the nose of the aircraft will go forward. If I get it too far aft, okay, if I come back up here, you can see that the nose will fly high, okay, and of course you stall the airplane. All right, so the CG, or center of gravity, should always be slightly forward of the lift vector, and it's actually a very, very small tolerance point, or range of tolerance, if you will, for where that balance should be. So weight is important, but just as critical is that the aircraft is balanced. And the pilot computes the weight and balance and controls it by loading the aircraft. Lift, again, is centered on the wing, or the center of pressure, or center of lift, and the balance is determined by the location of the center of gravity, which is the balance point of the aircraft. All aerodynamic forces acting in the three axes will act around the CG. So you can see here there's actually a slight moment here between the center of gravity and the lift vector. This one here will cause the nose, okay, will cause a rotation this way in pitch, will cause the nose to pitch down, and that's what you want. If you get the CG back here, okay, you create a nose up pitch, and then you stall the airplane. Okay, so there is a limit to the forward and the aft location of the center of gravity that keeps the airplane stable and controllable. Okay, so here's some terms. This is a Cirrus R22, okay, and I'll show you the Cessna one in a few minutes. Datum is the beginning reference point for measuring the center of gravity. For the Cessna 172, it is right at the firewall. For the R22, it's a few inches or in front of the nose of the aircraft. So actually 38.3 inches in front of the nose of the aircraft, you can see right here. Okay, so this is the datum line. Everything going this way is measured from the datum line. So if CG is here, okay, that's 100. It may be, 150 inches after the data line, and that's where your center of gravity would be. And again, each aircraft has its own datum line. It's determined by the manufacturer and set with reference to a part of the fuselage, such as the firewall, the nose of the aircraft, or a wing root. And you can see right here, the datum for this R22 is 38.3 inches in front of the nose, okay, and it's based on the center of gravity. The position location of any load in the aircraft is determined by inches from that datum. Okay, and let me pull this up real quick. Oops, that's not what I wanted. Here we go. Weight and balance. Yeah. Here's the datum for a Cessna 172. And the datum point where station is 0 is at the firewall, right here. All right. So the CG is measured to the rear of the aircraft from this reference point or the firewall. So that's your datum. So you can see right there. So the center of lift for this 172 is right here. Your CG, or center of gravity, is right here. Okay, so a little bit different. Okay. Each one, the 172, the Diamonds, the Cirrus R22, Beechcraft, they are going to have their own. And if you want to, you can Google the weight and balance. What's the reference datum for each of these aircraft, and that would help you out. Okay. Other terms: basic empty weight is aircraft fuel, usable fuel, fluids, and any other optional equipment. Ramp weight is the empty weight with fuel and the load before the engine start. Takeoff weight is the ramp weight minus any fuel that you've used for start, taxi, and takeoff, and run up. So landing weight is your weight after you've used your fuel en route. Useful load is the ramp weight minus the empty weight. So that's your crew, your passengers, cargo, baggage, and any fuel. Payload is the useful load. Of course, now fuel is not your part of your payload. That's your crew, passengers, and cargo. Usable fuel is a fuel that you can use. Usually it's about 5% less than what your tanks hold. And then you can figure fuel at 6 pounds per gallon. Okay, usable fuel left in the tanks, that's unusable fuel, that is too low to be drawn into the engine. So that for the Cessna 172, it's about 3 gallons out of 50. Okay. Weight and balance principles again, and I showed you with the ruler. The moment is the product of the force and a distance. Okay, if this is your center of gravity, this skunk is pushing down and making the nose pitch up. The bear is like the engine of the aircraft. It's making the nose pitch down. And where they are balanced, okay, that would be your datum, and that would be your weight. Okay, so this one creates a downward pitch or a counterclockwise rotation. This one, the skunk, creates a clockwise rotation. And if they're both balanced, you've got control. The aircraft, and I'll put this down here, just like I was telling you before, there's the center of lift for a 172. The datum is the firewall right here. And then your CG should be just slightly forward of the center of lift, which will create a little bit of a down pitch for your nose and to keep the airplane stable. So if you get a disturbing force, it will come back to level flight. So the center of gravity is the pivot point around all the moments applied. It acts like a fulcrum in a seesaw, and the weight of every part of the aircraft and control inputs create moments around that center of gravity. Moving the loads in the aircraft, again, will move the CG forward or aft. You never want the CG back here behind the center of lift, because the nose will pitch up and you'll stall and you won't be able to recover. So to maximize the stability, the CG should always be forward of the center. All right, of lift, that is. Aircraft center of gravity, okay, should be forward of the center lift, and so there will be a natural tendency to pitch down. So that down pitch actually increases the stability in the longitudinal axis along the fuselage. The positions of the CG and the center of lift, center of gravity, center of lift, are defined in inches from the data reference. Remember, the C-22 was 38 inches out here from the nose. The Cessna 172, the datum or reference is right here on the firewall. So it'll be a little bit different. All right, I will do another video, but you can use this slide. You'll have a quiz on this as well. This is the type of table that you use to do your weight and balance. And it's all about your moment will always be the weight of the force and then the distance. Okay, so it's going to be in inch pounds. All right, inch pounds. So to find your CG, you add up all your weights right to here. Okay, let me put that back. There you go. You add up all your moments right to here, and then divide your moments by your weights, and that'll give you your inches. Okay? And again, this is for a Cessna 172. You can give this thing a try. All right, so look at your class notes and the data for the 172. I posted the data for the 172. Here's how you do a weight shift. If you shift something from the back seat to, say, from here in the back seat all the way back to the cargo area, well, you're moving the weight aft. Okay? So you set up basically a ratio, the weight to be moved, the aircraft weight, the distance moved, and the distance armed. So here's your example problem. Take a look at that, and that will be on your quiz. Okay, operating again at high growth weights, when you do a turn, that's going to increase your stall speed. So the weight always must be opposed by the lift. And the lift must exceed the lift to establish a climb. Okay, so it's got to actually exceed the weight, that is. So excess weights will cause a CG shift because the increased demand for lift will cause a greater downforce. Turning flight will be affected because some of the vertical lift is not vertical but moves sideways in this angle theta. Okay, so it's actually going to affect the CG if you're overloaded. Okay, in a turn, the wings take on additional G forces, so if you exceed your design weight, then the structural stresses could damage the airplane. In a higher angle of attack, more power is required, and if you're overweight, you're not going to be able to overcome that excess weight. Because of the increase in angle of attack, stall speed will be increased. Okay, and when you turn, you'll stall the aircraft at a greater speed. All right, so here's some of the effects of CG. If your seat weight's here and your lift is here, then it'll tend to be stable, because anytime you have a disturbance, the nose is going to tend to drop. The nose will tend to rise, and if you can't get the nose back down, if the control forces from the elevators can't get the nose back down, then you're going to crash. Okay, you're going to stall the airplane. Again, the CG is too far forward. Okay, then the airplane's going to pitch down, and you won't be able to bring it back up. Well, the ground, that's where you're going to meet the ground. Okay, and if it's too far behind the neutral point, then the weight and CG will make the airplane become totally unstable. Okay, and it just totally messes up your tail forces. Okay, if the CG is too far aft again, you can see right here in the smoke tunnel, you're stalling the airplane. So you can see all of this turbulent flow, which you're not even creating lift. All right, so if you can't bring the nose back down and get laminar flow, you're in trouble. So if the CG is too far aft, the aircraft will tend to pitch up, creating an unstable aircraft in the pitch mode. And then the force required to create the moment to level the aircraft could be more than the tail section could generate through the elevators. Load factor will be high, and the aircraft could be overstressed, and then the aircraft could proceed to a catastrophic stall or a flat spin. Okay. All right, that concludes this PowerPoint, and then I will put out another one on doing a demonstration on a 172 weight and balance. Download the off of Moodle the 172 pilot operating handbook. That I've got the weight and balance section in there so that you can work on that on the quiz. All right.